Hello everyone. Today in this class I would like to discuss about asynchronous counters. These asynchronous counters are also known as ripple counters. Actually in the counters there are two types. One is synchronous counters and asynchronous counters. These two are differentiated according to the connection of the clock pulse given to the flip-flops. For the asynchronous counters, only one flip-flop receives the clock signal and the output of the first flip-flop is given to the clock pulse of the second flip-flop or next flip-flop. That is, continuously the output of the one flip-flop is given as a clock pulse to the consequences flip-flop. So that is a asynchronous counters. And if you are giving the clock pulse at a time to all the flip-flops, then it is a synchronous counters. Now in this class we would like to discuss about these asynchronous counters only, and these are also, as I said earlier, this is also known as ripple counters. Now let's discuss about these things. Asynchronous counters. So as I mentioned, as a counter, it needs to count from 0 0 to, suppose if I take 2-bit up counter, up, ripple counter. So I need to start from 0 0 and next it is 0 1, 1 0 and 1 1. The next cycle it should be 0 0. So it has to be continuously counting from 0, 1, 2, 3, then 0, 1, 2, 3. So this is called 2-bit up ripple counter. So that is a binary counter. Now, so this is a design of ripple counter. So in this we can see here I have taken two flip-flops because of I am talking about 2-bit up counter. Let's talk about 2-bit up ripple counter. 2-bit up ripple counter. So as I said, if it is a 2-bit, I just require two flip-flops. So here it is a one flip-flop and this is a second flip-flop. And so I use JK flip-flop and we can design these ripple counters with JK flip-flop, D flip-flop or T flip-flop. So in this I have taken a JK flip-flop in the toggle mode. So you already know the truth table for this JK flip-flop. So J, K, and it is Q of n plus 1. So the truth table for the JK flip-flop is, if J and K are 0, that is no change, that is Q of n. If it is 0 and 1, it will 0, and it is 1 and 0, the output will set to 1, and if it is 1 and 1, then it is Q of n complement. So whether initially if it is 0, then we can obtain 1, and if it is initially 1, we can obtain as 1. So this is a JK flip-flop truth table. Now J and K is initialized with 1, that means it's a toggle mode, and this first flip-flop is given the clock pulses, and the second flip-flop clock pulse is connected to the output of the first flip-flop. Okay. Now, so here two flip-flops for 2-bit counter, and first flip-flop I take it as a LSB and it will be taken as a MSB. The last one is taken as a MSB. Let's discuss about the working process of this 2-bit ripple counter. To understand this working process, first of all we know the sequence diagram or a timing diagram we need to draw. So let's discuss about the timing diagram. I am erasing all these things. Yes. Now, working of 2-bit ripple counter timing diagram. Okay. So now initially I would like to draw the clock pulse of the first flip-flop. So the clock pulse is taken as like this. Now, so this is a clock pulse. Now it is very important to triggering the flip-flop. The triggering methods are a positive triggering method, flat triggering, and a negative triggering method. So in this case, I am using a negative triggering method. So there is an advantage of this negative triggering method. Why? Because if the negative triggering method used, the flip-flop can hold the value for a longer time. And there is another advantage of this negative triggering method is immediate response and flexibility. Is these two are one of the most important advantages for this negative triggering method. One is holding the value for much time, and flexibility, and this immediate response. So these are the advantages of this negative triggering method. Now, so this clock pulse is given to the first flip-flop. Let me draw this output Q0 here. So I'm according to these clock pulses, I need to draw this. So let me draw this dotted line here, at least for the triggering place. Okay, so let me change the color. Right. So whenever the clock pulse is activated, the triggered, the first flip-flop will gives the output with the toggle mode. That means up to the triggering point, the value is 0. Whenever we are applied the trigger, it will be toggled to 1 up to the next triggering pulse. So in this way, this will be acted like this. Okay. So here we need to understand that the Q0 is changing the output value whenever we trigger. So up to the triggering, first triggering, these are first triggering, second, third, fourth, and fifth. So up to the first triggering point, the output is 0. Whenever we trigger, this 0 will becomes 1 because we use the toggle mode case. This Q0 is given to the clock pulse of the second flip-flop. So this will becomes the clock pulse for the second flip-flop, this Q0. So I will also consider the negative triggering clock. So I can write here. So this is the negative edge triggering, which is used as a clock pulse for the second flip-flop. Now I will draw the timing diagram for Q1 up to this clock pulse, triggering of this clock pulse, up to this triggering of this clock pulse, Q1 is 0. So whenever I triggered or whenever I activated the flip-flop 2, then Q1 becomes 1 and it will stay at 1 up to the next triggering pulse. So for the next triggering, it will become toggle mode from 1 to 0, then it will become 0 again. So this is the output of the second flip-flop. Okay, so now let me find the sequence, how the numbers will be counted upwards. So if it is a timing diagram from Q1, it's also here the negative triggering pulse will be given here. Okay, let's make it a table. So here I am writing clock pulse. Now it is Q1, here it is Q0. So for the 0th clock pulse, that means if there is no clock up to this point, so I am not triggered any flip-flop. So in this case, up to this point, it is 0 and Q1 is also 0. So that is Q1 0, Q0 is also 0. So now it is counted as a 0. Now once I triggered the flip-flop, first flip-flop, the output of the flip-flop becomes 1, and at the same time for the first clock pulse, the Q1 is still a 0. That is Q1 is 0 and Q0 is 1. So for the first clock pulse, after the first clock pulse, it will becomes 0 and 1. For the second clock pulse, now this will becomes 0. Now it will becomes 1. So that is Q1 is 1. Now it is 0. For the third clock pulse, it is 1. It is also 1. Now it is 1. Q1 is 1. Q0 is 1. For the next, it will becomes 0 and 0. That is for the fourth clock pulse, it is 0 and 0. Now if you see by decimal numbers, it is 1, it is 2, it is 3, and again it will becomes 0. So once the clock pulse is not there, it is 0, then next it will becomes 1 for the next clock pulse, next it is 2, 3, and repeated the sequence after the 4th clock pulse. That means it's a up counter, 2-bit up counter. It is very, very important to note down. And one more thing we can understand from this diagram is, if you see, let's say the frequency, if you see the frequency of the clock pulse, let it maybe f, why? Because it's a number of cycles per second, it's a frequency. If you see the frequency of Q0, so for this I can say up timing diagram, the time period can I say up to this is one time period. The time taken to triggering up to this point is t. Then the same time taken to this Q0 will take like this much of time. If the time becomes double, automatically we can say the frequency becomes divided by 2. See the frequency of Q1 diagram, Q1 flip-flop timing diagram, then it will becomes f by 4. So if the number of flip-flops increases, the frequency of each and every individual output will becomes it's like a f by 2 power n. Okay, this is a thing we can understand. The frequency will be reduced by a factor of 2. Right. So this is one of the important thing we can discuss here. Now let's discuss about 2-bit down counter. The only change we can observe in the down counter is the clock pulse for the second flip-flop. We are giving the clock pulse for the second flip-flop from the output of the first flip-flop, that is Q0. Now for the down counter, the small changes we can do is we can give the clock pulse to the second flip-flop from the Q0 bar. That means the second output of the first flip-flop. That is, if you see here, if you are giving this Q0 as a clock pulse to the second flip-flop, then it becomes a down counter. So let's see how this down counter will work. Okay, now let's draw the timing diagram for this 2-bit down counter. Timing diagram. Okay, let's take a. So as usual, so the clock pulse I would like to give. So it's a negative triggering clock pulse, and this is the clock pulse I have taken, and I will draw the Q0 as I draw previously. So I will draw these lines so that it is easy to draw. Okay, so up to this triggering point, it will be 0, then it will toggle mode. Up to this point it will becomes 1, then 0, then it is 1, then up to this point it is 1, 0, next. So this is the continuation cycle. So if it is a Q0, I can take it as a again negative triggering cycle. It will be the output of the first flip-flop. Okay. Now, so as I mentioned, the down counter, the Q0 bar is given to the clock pulse of the second flip-flop, right? The second flip-flop. So now I would like to draw Q0 bar. Why? Because this Q0 bar is taken as a clock pulse for the next one, right? So I would like to draw the Q0 bar as if it is Q0 is 0, it will becomes 1. If it is 1, it has to becomes 0. Up to this point it is 0. Now I can draw it as a 1. Now it is 0, 1, 0, 1, 0. So now it is a Q0 bar. So for the negative edge triggering, if you see, negative edge triggering is nothing but when you are moving from positive to negative, it is a negative edge triggering. So similarly, we are moving from positive to negative, it is called here the negative edge triggering. Okay. Now, so I would like to draw a timing diagram for the output of the second flip-flop, that is Q1. So if you see, the Q1 is here. The Q1 is initially 0 until this clock pulse is activated. So Q1 is 0 until this clock pulse is activated. That means up to this point Q0 will be 0. Why? Because we are triggering this flip-flop, we are triggering this clock pulse of second flip-flop, so we are triggering at this point. So up to this point it will be 0, then it will becomes 1. It will continue up to the next triggering pulse. Now it is 0. Now it is. So this is the output of the second flip-flop. Now let's make a table here. The clock. So Q1 and Q0 and the output. Okay, let's see. So for the 0th clock pulse, so that means before the clock pulse, the first clock pulse, that is first, second, third, fourth or fifth clock pulse. For 0th clock pulse, Q1 0, this is Q0 is 0. So why? Because this is Q1, it is 0, here it is 0. After the first clock pulse, Q1 becomes 1, Q0 is also 1. Now it is for the first clock pulse, it is 1 and it is 1. For the next clock pulse, it is 0. Sorry, it is 1, Q1 is 1, Q0 is 0. So that means here it is 1, 0 for the second clock pulse. For the third clock pulse, after the third clock pulse, Q0 is 1, Q1 is 0. So Q1 is 0, Q0 is 1. For the fourth clock pulse, it is Q0 is 0 and it is also 0. Now it is 0, 0. So if you see the decimal number, 0, 0 it is 0, 1 and 1 it is 3 and it is 2 and it is 1 and 0. So initially we started with 0, now it will become 3 and it is downwards, counting downwards, and for the next time it is repeated to 0 again. If you are giving again the clock pulse, it will become 3, 2, 1 and so on. So in this way we can design a 2-bit up counter and down counter. The difference between up and down counter is the connection diagram of the clock pulse. If the clock pulse is taken, if the clock pulse for the second flip-flop is given from the Q0, then it is the up counter. And if you are giving the clock pulse for the second flip-flop from the Q0 bar of the first flip-flop, then it is a down counter. Right? Thank you.